It's time for fun with math, and today we're going to talk a little bit about functions and, of course, how they change. So let's look at the first topic here, how do functions change? And it's actually pretty simple if you think about it. So when you think about a function, it can first do one of two things. It can go up or it can go down. So when a function goes up, of course, we say it's increasing. When a function goes down, of course, we say it's decreasing. And we always read a function from left to right. And so after we understand increasing and decreasing, we can start talking about relative maxima and minima. So the idea is if you put these two changes together, suppose you increase and then you decrease, versus you decrease and then you increase, you get a relative maxima or minima. So right here, this highest point is what we would call a maximum. And this lowest point down here, we would call a minimum. And we use the little adjective here, relative, because the graph could actually continue on and you could actually have a higher point. So let's suppose this continues on and goes up, 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 and then comes back down. So then right here, this is also another relative maximum. So that's an example of increasing, decreasing, concave up and concave down. Now when you increase or decrease, there's actually a couple ways you can do that. So one way is you could do it concave up, and another way is you could do it concave down. So for example, when you have something that looks like a U, like this, we say the function is concave up. Or better yet, you can think of this as being part of a smile. Put eyes right here, and you see that's a smiley face. So when there's part of a smile, the function's concave up. Versus when the function is part of a frown, then it's concave down. And again, you can see the frown here. Little eyes here, and you can see the frown right there. So now we know that that's concave down. So those are different ways to actually increase or decrease. You can increase in a concave up manner right here, or you could decrease in a concave up manner, or you could increase in a concave down manner, or decrease in a concave down manner. These are relatively important types of changes, so we can kind of think of make up an example here if you want. Let's make a sort of an axis here, and we can call this time. And over here we could put debt, let's say. So time versus debt. So suppose you're going between 2 points here. Let's start at 0 debt, at 0 time, and up here we'll have more debt. Now the way you actually go through these 3 points is actually important. So let's draw the 3 different ways. All right, so you could have this sort of concave up change, or you could have this sort of concave down change, or you could have no change at all. So no change in concavity at all, which would just simply be a straight line, which I'll draw the best I can here. It's supposed to be a straight line between those 2 points. And depending on the situation you're in, some of these changes are better than others. So like if you look at the concave up, right, this is actually very bad, whereas the concave down, I'd say it's bad because your debt's increasing, but it's not as bad. Right? It's not as bad because the debt's increasing, but it looks like the debt's going to sort of level off, and hopefully the debt will level off, and then of course then turn around and go back down. Whereas down here, with this concave up behavior, if that's your debt, we know it's really bad because your debt is not only increasing, it's actually accelerating, which means it doesn't look like it's going to turn around. It just looks like it's going to get worse. And of course here the straight line has a constant rate of change, really. So good or bad, I mean it's bad because you're accruing more debt, but at least it's not accelerating, but it doesn't look like it's also deaccelerating. So these are sort of examples where we care about concavity when we analyze something. Now notice if you change the context of this. So instead of debt, you say, you know, overall assets. So sort of how much money you have, in some sense, the value of what you have. Now concave up is good and concave down is bad. Because again, your overall assets are actually accelerating. Over here, this concave down is actually a deacceleration of your assets. All right, so again, just to review, the way we try to understand concave up, it's when a function's smiling versus when it's concave down, it's when it's frowning. We'll learn later on that you can actually rephrase these in terms of increasing and decreasing, in the sense that if you look at this concave up, what's really happening here, we'll talk about what's called the average rate of change, but you can see that actually the rate of change here, the rate of change along that point and the rate of change along that point are different, and it's actually increasing. So when the rate of changes increase, you get concave up. Whereas with the rates of change, you can kind of look here, this is sort of the rate of change there and the rate of change there. When the rates of change decrease, you get what's called concave down activity. But for now, just remember, when the function's smiling, it's concave up. When it's frowning, it's concave down. There's one last thing we need to talk about here, and that's inflection points. So they're kind of connected to maximum and minimum in a sense. So maximum and minima occur basically when you change from increasing to decreasing, or from decreasing to increasing. An inflection point is a change in concavity. So if we look over here on this graph, you can see that right here we're concave down. Let's do this with red. So you can see right here we're concave down. This is all part of a frown. And then somewhere over here we get a change, and it changes to concave up. So it's hard to tell exactly where it's changing concavity, but let's just guess it's changing right there, and then it goes concave up again. And so where you have that change in concavity, where it goes from that red to the green there, this is what we call an inflection point. It kind of reminds me of the word reflection, but it's of course inflection. And so inflection is where you change concavity. So it's where it's the point where the function changes concavity. It's the point where, let me write the graph. So the point where the graph changes concavity. And that's it. All right, so that's how functions actually change. They can either increase or decrease. When you have this phenomena, you get some relative maxima or relative minima. They can also increase and decrease in two different ways, basically, concave up or concave down. And with these two phenomena, you get inflection points. Let's take a look at an example, right, testing us on this. So here on the first example, we just want to basically use this graph and answer these sort of questions over here: the domain, the range, intercepts, increasing, decreasing, any relative maxima or minima, concave up, concave down, and inflection points. So let's just sort of review a little bit. And we'll use some colors here. So remember the domain, these are the input values. So you look along this graph and say, you know, what values of x basically can you plug in and get a graph above or below. And so notice these arrows mean, you know, go up all the way to the left, up all the way to the right. So the domain looks like it should be everything. So our domain here would be negative infinity to positive infinity. And then of course the range, instead of looking at the inputs, the x values, we look at the outputs, the y values. So instead of going along the x-axis, we go along this y-axis. And if you start down here, it looks like it starts right here at negative 27. So there's nothing below negative 27, so we're going to start there. It's a closed circle, or basically there's no open circle, so we know we include the endpoint. So it includes negative 27, and it goes all the way up. So everything on the y-axis above negative 27 and including it. So our range is negative 27. Make sure you include it, all the way up to positive infinity. Remember this notation, this interval notation. It's actually shorthand for a set. So we don't want to write it because it's a little bit complicated, but I'm going to show you what it is. So remember, this is actually the set of all, in this case, all y, such that negative 27 is less than or equal to y. that's what that looks like. And you can continue if you want to write here less than infinity to show you how the interval notation actually works. But that's what it's actually equal to. But remember, to avoid the set notation, we like to write it in this interval notation. All right, so let's clear off what we've written here. And let's go down to the intercepts. So here we have an x-intercept and y-intercept. So the x-intercepts, and notice it could be plural, could be multiple. It's where you cross the x-axis. So you cross here and you cross here. And they're actually points. So it's the point 0, 0, and the point 4, 0. Remember, it always goes input, then output. It's alphabetical. So 0, 0, and then 4, 0 are my two x-intercepts. And then the y-intercept is where the graph intercepts the y-axis. Now, if there is one of these, there's only one. It does happen to be one right here. So it has an x and y-intercept in the same spot. And again, it's 0, 0. So here we'll put 0, 0. And so that's an x-intercept and a y-intercept. Now, this is sort of review from what we did last time. And so now we get to some of the new stuff. So for the new stuff, we're going to talk about increasing and decreasing, and I'm going to draw this on the graph. So if you look at the graph here, you notice first thing you're doing is you're decreasing. So you're decreasing, you're going down, we're left to right, decreasing, 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 decreasing. Something kind of funny happens here, and we'll talk a little bit about it in a bit, but this is definitely decreasing, 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 and then you change from decreasing, and the graph starts to go up. And so that's increasing. So increasing, 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 increasing. And so now we want to write this down. So the way that we write this down is we're going to use interval notation, and you're always going to tell me the inputs basically. And you'll notice that it's always the inputs unless you're talking about the range. For the range, you give me the outputs, but for everything else, it's always the inputs. So it's increasing on this green piece right here, and if you look above it, it starts at x value 3 and goes all the way to the right. So all those x values, and this is a parenthesis, we're not going to include endpoints here. So we'll start at 3, don't include the endpoint, and go to infinity. That's where it's increasing. And then it's decreasing basically everywhere else. So it's decreasing, you can see the red graph here, it's going down, 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 down. So it's decreasing all around here. And there's actually two ways to write this one. So a lot of times you guys will just write this as negative infinity to 3, which I'd say that's great. I agree. Negative infinity to 3, those x values, if you look above, the graph is going down. But you could also write this, if you want, as negative infinity to 0, union 0 to 3. And the reason for that is because if you look kind of right here, what's happening at 0, it's kind of leveling off. So in a sense, it's really not increasing or decreasing at 0 right here. So you could actually split it up if you wanted to kind of point out that phenomenon going up. But you don't have to. So I always tell you on the test, if I ask you a question like this is certainly the correct answer. You can write that. But if you write it like this, I'll give you a +1. Little bonus point. Right, so for pointing out some sort of slightly strange phenomenon going on there at that point. All right, so now we have relative maximas or minimas actually where you change color. So you can see here you only change color once. There's only going to be one maxima or minima, and you can see there's really no maximum. There's no highest point relatively, and there is a relative minimum. So relative minimum occurs here. For the minimum, you have to give me the output. You don't have to give me the input if you don't want to, but you have to give me the negative 27. I just tell you guys, just write down the input and the output. So f of 3, because the input value here is 3, and the output value is negative 27. And so give me both input and output. That way you can't make a mistake. But you have to give me at least the negative 27, because by definition, minimum maximum values are actually output values. All right, so moving on, we want to now talk about concavity. And so we're going to do the same thing again here. I'm going to color this. I'm going to color it green for concave up and red for concave down, because green is good and red is bad, of course. And concave up is part of a smile, and concave down is part of a frown. And so we'll start here. from left to right, and it's definitely part of a smile. You see this right here is part of a smile. If you don't believe me, you can put little eyes right here and say, yeah, that thing's smiling at me. And so this is all concave up right here. But then it turns around and goes concave down. And again, if you don't believe me, just put little eyes right here, and you'll see that's a sort of a sad face, so that's concave down. And then it changes concavity right about here and turns back into a smile. So again, you can put little eyes here if you like, and you can see that's part of a smile, and so that's concave up, and it continues to be concave up forevermore. And so when I'm writing when it's concave up, remember you're always going to give me input values, so we're going to use this interval notation, so all this stuff below the green or above, right, not including the endpoint, and then pick it up over here at 2 because it's green above or below after you pass 2, not including the endpoints. So here I'll write down all the way to the left, so that's negative infinity, until you get to 0. Union, pick it up at 2 again, and go all the way to the right, so positive infinity. And so that's where the function's concave up. And of course, in between, it's part of that frown, so it's concave down. So between 0 and 2, those x values, if you look at the graph, you'll see it's concave down. So 0, comma, 2. You do need to be a little bit careful with this sort of interval notation versus coordinate notation. So notice right here, this is the coordinate 4, 0, not the interval 4, 0. Of course, you can't have an interval 4, 0 because it has to go in order. But from the context, right? So from this context right here, the fact that it's an intercept, you're supposed to understand that the answer is a point. Whereas down here, when you ask for concave down, 0, 2 is not a point. It is not a coordinate pair. It is an interval, right? It's sort of a continuous bunch of x values. Right, so finally, we want to talk about inflection points. And inflection points are where you change concavity, or again, you can say where you change color. So here I went from green to red, so that must be an inflection point, and red to green, so that must be another inflection point. Or you can say I went from concave up to concave down. That's really why it's an inflection point, or concave down to concave up. And so inflection points occur at 0, 0. And then at this point here, right, so it's 0, 0 right there, so you can see it. And then this point right here, which is you go over 2, and then you go down negative 16. So 2, negative 16. So 2, negative 16. So those are the two inflection points. And again, these are points. They are coordinate pairs. They are not intervals. Okay, so we want to go now that we understand basically how functions change a bit. Now we want to talk a little bit about how do we measure this change. And we're not going to get too deep into this, but I do want to introduce the ideas. So one way to measure this change is, of course, by simply looking at the graph. But what if we don't have a graph? What can we do? There is a way to use the formula to figure out if it's increasing or decreasing, or concave up or concave down. And so to do that, we use a notion of what's called average rate of change. And typically this is going to be given to us on some interval. Here it says A to B. The idea is actually really simple if you think about it. So the idea is if you give me a function, I don't care what it looks like, but here's just some sort of random function, f of x. All right, and you want to try to understand how it's changing. One way to do that is just take 2 points on that function. So here's 1 point, and here's another point over here. And so the first point, we can say the input value is A, and the second point, we can say the input value is B. And of course, if the input value is A, the output value is f of A. You just plug A in for x. And for this one, the output value is f of B. And what you want to know is, how are these 2 points, how are the values changing between these 2 points? And so we do something that's called the average rate of change. So this has an input value of A, an output value of f of A, and this one has an input value of B and an output value of f of B. And so to compute the average rate of change, you simply take the change in the output and divide it by the change of the input. And so we write this kind of fancy, and we're going to say, oh, delta f, and delta means change in, so change in the output over the delta x the change in the input is simply you just take the difference of the outputs and subtract the difference of the inputs and divide difference of the outputs and divide it by the difference of the inputs, so B minus A. And so that's the formula for the average rate of change. Do you have to memorize this formula? A lot of students do. You can actually think of this in another way as simply being the slope of the line through those 2 points. So you can think of that as being the slope of the line between those points. So some students say instead of functional notation, they'll just say y sub 2 minus y sub 1 over x sub 2 minus x sub 1, because that's the formula they remember for the slope. Formulas are important, but it's really the ideas you want to remember. And average rate of change is a common sort of idea. Usually the example I'll give you is like, hey, if you made $1,000 over the last 10 weeks, what did you make on average each week? And so you just take 1,000, of course, and divide it by 10. 1,000's your output, your input is 10, and of course you get $100 per week on average is what you're pulling in. Oops, not year, but week. So I mean, this is something that you can compute easily. You can also do this in miles. You can say, oh, I went 200 miles in the last 5 hours, so how much did I go each hour? So you do 200 divided by 5, and you get about 40 miles per hour on average, which means you're not going very fast, but that's the idea. Let's take a look at an example of using this. And so we're going to actually go back to the problem we just sort of did. So we have the same graph right here. So this is the same graph we had before. And we want to do is find the average rate of change of this function from 2 to 4. And it's easy to draw this on the picture, what you're actually doing. So we're going to do that. So x equal 2 to x equal 4. Well, here's x equal 2. So here's the point on the graph. And here's x equal 4, and there's the point on the graph. So what you're really doing is just computing the slope of that line. And so we can write down the formula to practice, functional notation, this delta notation. So delta f over delta x. And so what we want to do is take f of the final, which is 4, minus f of the initial, which is 2, and then divide by the change in the input. So 4 minus 2. So change of output divided by change of input. And it equals, and so to find these values, of course, we're just going to read them off the graph. So this point is 2 comma negative 16. And then this point up here, of course, is 4 comma 0. And so when I plug in, f of 4 is the output. So the output is 0 here. So I'll put 0 for f of 4. Minus f of 2. F of 2, again, is the output, and that's negative 16. So I'll put that in parentheses, negative 16. And then on bottom, of course, 4 minus 2 is just 2. And so this is going to be equal to negative, so 0 minus a negative is a positive, so positive 16, divided by 2, which of course gives us the number 8. All right, so that's the average rate of change. Notice the number is positive, so that's actually telling us how the function's changing on average. And since it's positive, we can say that this means that the function is not decreasing, but increasing on average on 2, 4, on the interval 2, 4. So notice it does decrease here. So saying that it increases on average doesn't mean it can't decrease. It just means overall it's increasing on that interval from 2 to 4. In addition, you can actually use the average rate of change to figure out if it's concave up or concave down. So let me give you an example of this. So it says the average rate of change on 2, 3 is less than or greater than, we have to circle one of those, than the average rate of change on 3, 4. So let's look. So here's 2, 3 right here. If you look at the average rate of change, just find the points on the graph that correspond to 2 and 3, and you can see here's the average rate of change. It's the slope of that line versus the average rate of change of this blue line between 3 and 4. So here's the point when you plug in 3, here's the point when you plug in 4, and then you just have to ask yourself the question, how do those two slopes compare? How do those two rates of change compare? Well, the green line's going down, so that means the average rate of change has to be negative, whereas the blue line is going up, so the average rate of change has to be positive, so it has to be less than. Right? So the average rate of change here is going to be negative, because you can see that it's going down, and then the average rate of change of here is going to be positive. And a negative is always less than a positive, and it's positive because the blue line's going up. So this would seem to imply that the function is actually concave up. Right? So when the rates of change increase, you get this sort of concave up behavior. And when they decrease, you actually get a concave down behavior. That's not too important right now, but I wanted you guys to see that you can actually use the average rate of change to figure out if a function is concave up or concave down. What is really important, though, is that you can actually calculate an average rate of change from a graph, or let's look at the next example, from a formula. So this is a more standard type of problem. So here, what we want to do is we want to find the average rate of change of the function on the given interval, and then draw a picture of the average rate of change that we are calculating. So let's do that. All right, so here's our function, x squared minus 9 equal negative 2 to 4. And so let's just follow the formula, right? So, and then we'll actually draw a picture of what this is. So delta f over delta x is equal to, so change in the output over the change of the input, is equal to f of 4 minus an f of negative 2. Right? Always the final minus the initial, so 4 is the ending point, negative 2 is the starting point. So f of 4 minus f of negative 2. And the same order on the bottom, 4 minus negative 2. Don't screw up the order or you will screw up the problem. But you should be able to catch your mistake if you draw a picture, which we're going to do in a minute. So let's just do what this says. F of 4, it says plug in 4 for x. We're not going to use a calculator to do this because we want to make sure we understand function notation and how to compute with it. So where I see an x, I'm going to put a 4, and so I put 4 squared minus 9. Minus, now I'm going to plug negative 2 in for x, and so I'm going to put this in parentheses because it's going to take off the whole thing. So negative 2 quantity squared minus 9. And then that's all divided by a 4 minus a negative 2, which of course is a 4 plus 2. And I'm going to jump over this picture here and go to the other side. So this is going to be equal to then what? So 4 squared is actually 16, and then minus 9. Minus, in parentheses, negative 2 quantity squared is a positive 4, because the negatives cancel, negative times a negative is a positive, and minus 9. Notice I'm just doing simple calculations. I'm not trying to rush it, right? Because otherwise I'm going to make mistakes. And then I have 16 minus 9, which is 7. And then minus, then what do I have here? I have 4 minus 9, which is a negative 5. So in parentheses, a negative 5. All divided by 6. And so that's going to be equal to, it's equal to what? So 7 minus a negative 5 is really 7 plus 5. All over 6, which equals 12 over 6. Oh, that's a nice number of 2. Right, so my answer is equal to 2. Now I can check this answer by simply graphing it on my graphing calculator and seeing what I get. So let's do that. So on your graphing calculator, let's turn it on and then hit y equals. And what we're going to do is we're going to graph this function. So we're going to plug in x squared minus 9. So x squared and then minus 9. So there's the formula. And then for the window, we're just going to have a negative 10 to 10 window. If you hit window and you see something like this, it's not set up right. I know it's negative 10 to 10 because they're giving me the window, negative 10 to 10, negative 10 to 10. So you can put it in manually if you want. Hit negative 10, enter, 10, enter, negative 10, enter, and 10, enter. So you can do that if you want. You could also just go to zoom and go down to Z standard, which is basically zoom standard, which means zoom in the standard window, and hit enter, and it'll do the same thing, negative 10 to 10. So there are two ways to kind of get the standard window. So that's what the graph looks like, and so we can trace this right down here. And it doesn't have to be perfect, right? But we can just kind of trace this out. It goes down, comes up like this. And what we're doing, we're starting at negative 2 and going to 4. So you can actually hit trace and hit negative 2 enter, and it'll tell you where that point is on the graph, -2, -5. And then what we can do over here is we can actually put that point on our graph, right? So here's the point on our graph, -2, -5. And then go back to the graph and hit 4 now and enter. And it'll put that point on our graph. There's 4, 7. So that's the other point on our graph. And so we can come over here and put another point right here. It's doing it red again, I guess, right? So right here, we can put 4, 7. And what you're computing is simply the slope of this line between these 2 points. So here's the line, and you're computing the slope, or if you want, the rate of change between these 2 points. And you can see 7 minus 5 is positive 12, 4 minus 2 is 6, 12 over 6 is 2. So it checks really fast, but you don't want to avoid the computations, right? So make sure you can actually do this by hand so that when we get to the algebra later on, you're able to do it. Let's do one more together. So below this, we have this function, g of x is equal to 1 divided by x minus 3. And we're going to do this on -1 to 5. So again, let's practice the notation. So delta, instead of delta f, I'm going to put delta g, because my function's g. Realize they use f for function, because it stands for function. And the next letter in the alphabet's g, so g of x is used. And sometimes they'll even use h of x to represent a function. They just kind of go alphabetically. So delta g over delta x. And so what does that mean? It means take the change in the output over the change of the input. So you're going to do g of 5 minus g of -1, all divided by 5 minus a -1. Right. This step is really important. It's a step that students often skip. And what happens is if you skip this step is you don't learn how to read functional notation or really work with functional notation. So it's real important that you practice this and then sort of just do what it says. So what does it say? It says plug in 5. And again, we're not going to use our calculator. We're going to do this by hand to make sure we can do all the basic computations, the basic arithmetic. So wherever I see an x, I put 5. So 1 divided by 5 minus 3. And then minus, then plug in -1. So 1 divided by -1 minus 3. And then that's all divided by 5 minus a -1. So it'll be 5 plus 1. Just do some basic calculations sort of one at a time. So this is 1 divided by 5 minus 3 is 2. So you have 1/2. Minus 1 divided by -1 minus 3 is -4, so 1 over -4. And then that's all divided by 6. So that's going to be equal to, now a minus is a plus, so it's going to be 1/2 plus 1/4, all divided by 6. Notice I'm not using my calculator because I want to make sure I understand how to do basic arithmetic so then I can learn how to do algebra, basically. So here I need to get a common denominator, which is actually pretty simple to do. So this is a 4. I'm going to turn a 2 into a 4. I can do that easily by multiplying top and bottom by 2. And so I get 2/4 plus 1/4, all divided by 6. And so I have 2 of these plus 1 of these, which is 3 of these. So you get 3/4, all divided by 6. Remember, 6 is really 6 divided by 1. And when you divide by a fraction, you multiply by the reciprocal. So 3 over 4 times 6, oops, not 6, but 1/6, because the reciprocal of 6 over 1 is 1/6. So times 1/6. And so what do I have here? I get 3 divided by 24, which will simplify to 1 over 8. Because remember, 24 is actually 3 times 8. So 3's actually cancel here, and I get 1/8. So that's my answer. I would like to check my work to make sure I actually did it right. So I'm going to draw a picture. And so to draw a picture, I go back to my calculator, I hit y equals. I'm going to clear this out. I'm going to do 1 divided by. Now here's where you have to be careful. Here's where you have to understand how order of operations actually works. On the bottom here, you can't just type x minus 3. If you do, it'll be wrong. What you need to do is type a parenthesis and then x minus 3. Because the x minus 3 is all in the denominator. So now it's the function 1 divided by all of the stuff, x minus 3. And my window's already set up, but if it wasn't, I could just go to zoom, since it's a standard window, go down to Z standard and hit enter, and you'll see the sort of graph of this function. Now when I draw it on here, I'm not going to draw it exactly the same way because I just want to get the idea down. So it looks something kind of like this. It goes down here, if you're familiar with graphing these types of functions, there's actually a vertical asymptote right here. And it comes up here and goes down there. That's what it sort of looks like. You can look on the calculator here and see. And so we went from -1 to 5. So what I can do is I can trace this thing and type in -1. And it gives me at the point -0.25. And so on here, what I can do is I can just put a point here. And I can call this, it's going to be -1, comma, -0.25. So all right, -1/4. So -1/4. And then I plug in the next point, which is 5. So I'm going to 5. So hit 5, enter, and it'll tell me that the output is 0.5. So over here on my function, over here at about 5, so 5 comma, I get out 0.5, which is 1/2. And so remember what we're doing, you can kind of look at this, we're just trying to compute the sort of rate of change between these 2 points. And so you just kind of draw a line there and say it's just the slope of that line. So it's a change in the output, 1/2 minus -1/4, divided by the change of the input, 5 minus -1. And you'll see you basically get out 1/8 on there. And if you want to check it on your calculator, you could. Right? Since you have the numbers down, you could just say, okay, well, I'm just going to check this thing. I'm going to say, okay, 1 divided by 2, I'm going to put this in parentheses, minus a -1 divided by 4. Notice when I hit the negative button, I have to that negative sign, not the minus. And then divided by left parenthesis. And then if I start with 1/2, you start with 5. 5 minus a -1. So just use the picture. Change in the output, the change in the input. And you get this number 0.125. Now, I don't know if that's 1/8 or not, but I can check it. 1 divided by 8 is equal to 0.125. You could also math frac this thing. If you hit math and enter, it math fracts it and puts it in a fraction form for you. But again, don't use your calculator to avoid the computations. Otherwise, you won't be able to do the algebra later, which is really the hardest part of this class. Okay, so let's just review real quickly what we did today. We talked about how functions change, and so basically functions can increase or decrease, or they can be concave up or concave down. From increasing and decreasing, you get relative maxima or minima, right? So very highest points or very lowest points. From concave up or down, you get inflection points. That's where you change concavity. So we can look at a graph and we can tell you all these different types of phenomena occur, but what happens if you don't have a graph? How can we measure this? Well, one way we can measure this is we can use what's called the average rate of change. And so if the average rate of change is positive, this thing's going to increase. Where if the average rate of change is negative, it's going to decrease. And we can even tell concavity by using the average rate of change, although it's a little bit harder to figure out. But you can kind of think about it. It's like here's a function, and it's concave up. Why is it concave up? Because if you look at some points, so look at this point and this point, you can calculate an average rate of change using those 2 points. And then you come along and compute another average rate of change using that point, and you see that the average rate of change on the blue line is smaller than the average rate of change of the green line. So that gives us what's called a concave up activity. All right, so we talked then about this sort of average rate of change and how to compute it. And then in the next video, we'll get to this last topic, which is called the difference quotient, which is in some sense a generalization of the average rate of change. But we'll talk about this next time.